Hello. Wow, Monday morning again already. Wow, what happened? So, morning. All right, so starting another week already, and so let's get back to where we were. Now, let's go to Moodle and see what we've got. Um, right over here, we have in our Moodle account. Here we go. So we were partially through 5B. And so we'll carry on with that today. And then in addition to that, we also have a couple of new videos to watch today, very fun videos about the history of math in general and about this content in particular. And also one other thing I just want to point out, now that everything's in place, if you go to my YouTube account, if you're looking for the videos and you're saying, well, where are they? Here's what you have to do. Go to the playlists. And our playlist, of course, would be right here. Okay, Math 1060, the 8:30 session. And if you look at the playlist, you'll see here are the videos right here. So you can just download them and watch them whenever you feel like it, if you want to. It's always optional. This is just exactly what we were doing in class. And so a couple, ooh, look at that. Nobody's watched them yet. Well, there they are. But that's because you've all been here all week. And so that's good. But you never know when you may want to review them, or else if you just can't be here one morning, well, that's okay. That's what the videos are for. So everything's here, and I hope you will have no trouble finding them. Anyway, so let's get to it. All right, so 5B. Let me just open it out of my file folder here. Whoops. Oh, what am I doing? Right here. Okay. So we've got 5B still to go. Yes, so we were partially done with it. We just got into it a little ways. We were looking at radicals and roots. And so we didn't get all that far. In fact, I think we stopped. I know we definitely were talking about perfect squares. And I think that may be about as far as we got. So, all right, right about here, why don't we start here? So let's see, let me just quickly save this. Today's the 8th. And let's pick it up where we left off now. Hello. Oh, vellum equals sheepskin. Oh, that's right. Yes, it is. That's an interesting, that's because we're talking about Archimedes. Yes, the book that was recovered. This was about 10 years ago now. In fact, maybe we could find an article about it in the New York Times or something. I don't know exactly how to look for it, but Eureka's Secret Book by Archimedes discovered. In what can only be called an incredible feat of conservation technology, a 1,000-year-old text by Archimedes is now on view at the Walters Museum in Baltimore. The book is a palimpsest, meaning the original text was erased and written over, but is still visible, even if only faintly. Yep. Oh, you never know what they're going to be able to do next. Wow. So there it is. It's not in very good shape. But if you want to read up about it, here it is. Yeah, and speaking of vellum, I was once fortunate enough to be in London, and I managed to get myself into Salisbury Cathedral, where they have one of the 4 surviving copies of the Magna Carta, if you can believe it, which, as you know, was signed by King John in 1215. And the thing about it, it was written on vellum, because that's what they did in those days. And because of that, it's still in really, really good shape. Only problem is there's not much room on a piece of vellum. And so the whole thing, the writing is so cramped and so tiny, and it's all in Latin, that it's impossible to read it, but it's there and you can see it, and you can at least say that you've seen the Magna Carta, and it's a pretty big deal. But don't try to read it because it's not going to happen. You need a magnifying glass and a very good knowledge of Latin. Otherwise, it's not going to make any sense to you. But it is on vellum, and that's why it survived all these years. In fact, it wasn't too long ago that we had the 800th anniversary of the Magna Carta. So anyway, so let's get back to this. Now, you recall last time we did mention that the square root of a number, like the square root of x, is really just another way of saying square root of x, this symbol is simply the same thing as x to the 1/2 power. Now, we could write a 2 here. Usually, for whatever reason, we leave it out. But if you want to be super technical, there really does need to be a 2 here to distinguish it from any other roots that you might need to use. Like, for example, the cube root. Okay, if you've ever heard of this before, there is such a thing as a cube root. Now, this time, we need to write the 3 to make it crystal clear that this is not a square root, but a cube root. And so this is equivalent to x to the 1/3 power. Now, if you look at your iPhone calculator very quickly, you'll see in the upper left-hand corner, let's see, where is it? Oh, no, it's like over on it's in the 3rd row, 3rd from the left. There actually is a button on this calculator that will help let you take cube roots directly. It's got 3 buttons right next to each other. It has the square root, of course, written as x, and this means to the 1/2 power. It also has a cube root button. And for any other roots you might need, it has this button. And that means this can be anything that you specify. You can tell it what you want to do with that. You can make it 3 or 2 or 4 or 8 or -3 or 1/9. You can do whatever you want with it. So just be aware that those buttons will enable you to do what we're doing here. All right, it's very convenient, very nice and easy. Of course, you have to get practice using it. Every calculator approaches this a little differently, but it's set up to be as user-friendly as possible. Okay, now, what is a cube root all about? Well, all right, the way this works is since 2 to the 3rd power, or 2 cubed, it's pronounced, equals 8, and that's because this actually means 2 times 2 times 2, 3 times, that equals 8. The reverse of this would be the cube root of 8. Okay, so in other words, the cube root of 8 means that some number, actually, sorry, let me do this all over again. There is some number which, when multiplied by itself 3 times, gives us back 8. So if you want to check this out on your calculator, you can go ahead, just type in 8 cubed. Now, if you're going to do this, let me just double check this one more time. It's important to know what order to do this in. So in this calculator, you hit the 8 and then you hit the cube root button. In some calculators, it's the other way around. So on our calculator, just make sure you hit 8 and then the cube root button. And you don't even need parentheses. You don't need the equal sign. It automatically comes back with the 2. All right. So once again, this is the cube root, or x to the 1/3 power, and this is how we interpret it. And over here, you see this is how we calculate it on our calculator. All right. What about this one? Okay, well, if we can have a cube root, this one is called the 4th root. We ran out of names, apparently. After this, this is now simply called the 4th root. I'm sure there might be some other more exotic name for it, but we can simply refer to it as the 4th root. And that's x to the 1/4 power. Okay, so how would that one work? Well, how about this one? All right, let me just leave that for a second. X, the 4th root of x, is simply x raised to the 1/4 power. So you're starting to get the sense here, and you're right, that whenever there's a square root sign here, or radical sign, I should say, you're going to raise your x to some fractional power. And that is absolutely correct. So anyway, let's take this case. 3 to the fourth power, which is 3 times 3, 3 times 3 times 3 times 3 equals 81. Okay, so that implies that the fourth root of 81 must be 3. Okay, and that's how that works. And so again, if you go to your calculator, this time you have to specify the order. All right, so in other words, if you want this one, there's no button on this calculator for the fourth root. So what you're going to do is this. You're going to type 81. See, let me just make sure I remember it myself. Yeah, this is how it works on this calculator. Type 81. Sorry about that. 81. Hit the Y. The Y. This, you can think of this as the. Hold on. In English, technically, this would be pronounced as the, believe it or not, the Wythe root of X. I know it sounds weird. And then what you have to do then is specify that this is the fourth root. So in this calculator, what you're going to do is type 81, hit the root button, and then hit the 4, and then hit equals. And that will produce your answer, which is, of course, 3. But this time, unlike before, you must introduce and specify the 4, and you also need the equal sign, whereas before that wasn't necessary. Okay, with the cube root that we had earlier, this is all you need to get the answer. That's because this is a predefined function. This is a general function where you have to provide more information. All right, so make sure you can do that. Take the fourth root of 81, make sure that it's working, and it's giving you a 3. Okay. All right, now, as you can probably guess, it goes all the way up to infinity. I mean, there's any number of roots are possible. So in general, we can write this expression where n can be anything. Okay, so this equals 1 over, this equals x to the 1 over n power. Okay, and so n can be anything. It's typically an integer, but it doesn't have to be. Okay, so this is the most general expression. And sometimes you hear these given a special name. If you look at the x to the 1/2, x to the 1/4, x to the 1/6, x to the 1/8, you notice how they all have an even value in the denominator. Over here we have x to the 1/3. This is x to the 1/5, x to the 1/7, x to the 1/9. These are collectively known as the even roots. And these are collectively known as the odd roots. Now, here's an interesting twist. As far as this is concerned, it is possible to take an odd root of a negative number but not an even. Okay, so with the odd roots, we can actually have negative numbers, not so with the even roots. All right, so if you go to your calculator and you take, let's say you try to take the cube root of negative 8. If you try it, you can try it right now with your calculator. Try to take the cube root of negative 8, and it'll come back with negative 2, because negative 2 times negative 2 times negative 2 equals negative 8. But don't try that with the square root or the fourth root, because you'll just get an error message. All right, so just be aware that you can take odd roots with negative numbers. Also, one more thing on this calculator, to make a negative number, here's what you don't want to do. Use the minus sign. There's a special button called, it looks like this, okay, plus/minus. To make a negative number, and this sounds backwards, but what you're going to do, if you wanted to type a negative 8 number, you would write 8 followed by this sign. And in the window, you'll see that it's turning it into -8. So this is one of the quirky things about this calculator, although many other calculators do the same thing. To make a negative number, don't type -8, type 8 followed by this symbol, which you'll find, by the way, in the extreme upper right-hand corner next to the C. All right, so make sure that you can do this right now. Try to take the cube root of -8, because this will test you in several very important ways. All right, is everyone doing that? Very good. Okay, now if you have a more advanced calculator, like the Texas Instruments calculators, they tend to be a little bit different than this. They will have a negative sign that actually comes before the number. Okay, but here on the iPhone, you have to have the number itself, and then you make it negative with this button. Because what it's really doing, it's not really a negative button at all. What it really is a button that says change the sign. So if your number is currently positive, it becomes negative. But if your number is currently negative, that will make it positive. Okay. All right. Now, the next thing we want to consider is algebraic operations that we can perform on these radicals. For example, what can we do? Well, can we multiply radicals? Yes. Can we divide them? Yes. Can we simplify them? Yes. We can do all of these things. And then later on, we'll finish up with addition and subtraction. Now, there are certain ways we can do this very efficiently. And so that's what we're going to try to focus on. So, for example, what if I have, and by the way, let's just assume these are two positive numbers. If I have the square root or radical of a product, I can break it up into the product of these individual terms. So, for example, if I had 75, I could rewrite that as 3 times 25, and then I could rewrite it like this. And it means the same thing. And then, of course, this one is 5, so I could take it one step further and write it like this. Now, if you notice, by convention, when we have a number that contains a radical, we typically try to put the whole numbers outside of it and then write this last. In other words, this expression is technically correct, but you don't usually write it like that. Normally, it's written like this. Okay, this is the preferred form, basically. Just like if you have a fraction like this, you typically just reduce it as much as possible. Not that there's anything wrong with 2/4, but 1/2 is the way to go. The same thing holds with the radicals. There are rules that we'll see that govern the best way to express radicals. Mathematicians are very serious about this. This is important to them. The order in which you write these. They would say, "Oh, this is awful. Don't do it like this. This is what we want." Okay, so now this can help us in certain cases simplify our results. This is a very convenient property, as it turns out. All right, so what are we? Oh, here we go. Here's just some simple examples. So you can see all we're doing is breaking this up into its factors and then splitting it up further. And whenever possible, we always like to simplify. In other words, you don't just leave it like this. This is, of course, 2. So we should simplify radicals. Whenever possible. Okay, it isn't always possible, of course. And in fact, I'll tell you what else we probably would do. Normally, this process would not be undertaken unless there's a good reason for it. In other words, mathematicians would agree that it's better to have this expression than this one. You want to have the smallest possible number under your radical sign. Again, not that these numbers are wrong. This is not an incorrect number. There's nothing wrong with it, but it's usually preferred to have the radical as small as possible. So at the same time, though, since these are both prime numbers and we can't simplify them any further, under normal conditions, if you have an answer radical 10, there would be no need to simplify it like this, because if anything, this is making the result messier. So while this statement is correct, it isn't something that we would normally do because it doesn't give us any simplification. We're down here. Obviously, this is simplifying to a certain degree. It's reducing it to 2 radical 3. So we would normally carry out this step, but not this one. All right. Just again, it's all about the simplification. It's just, this is just the way things are done in math. All right. What about simplifications? Now, we already know about perfect squares. Okay, the perfect squares give us an integer when we take their square roots. That's why they're called perfect squares. So what happens when we have a radical, a fairly large radical? The larger the radical is, typically, the more likely it is that we can simplify it. So here's some good examples of this. Now, of course, radical 40 could be written as radical 8 times radical 5, but this doesn't really help because it's not simpler, is it? But what we can do instead is use 4 and 10, and the reason why we choose 4 and 10 is because 4 is a perfect square. Okay, and so therefore, look what happens to it. We end up with 2 radical 10, and so a mathematician would prefer this to this, because remember, one of the things we're trying to do is make sure that the radical is as small as possible. All right, 2 radical 10 would be preferred to radical 40. Now look at this one. It may not be immediately obvious, but if you were to write out a list of all the factors, you'd say, oh, wait a minute, look what we have here. A perfect square is one of the factors. Wonderful, because look what happens. This now reduces to 6 radical 7. And that, as I said before, would certainly be preferred to this. Not that they're not the same thing, but this is what we prefer in math. Simpler is better, okay? Especially when it comes to radicals. And then here's another lesson, which again, you may be surprised to note that one of the factors is in fact a perfect square, which is 49. See, it's not always immediately obvious. And that's good because then look what we can do with it. We end up with 7 radical 5, which of course is a preferred form to this. Part of the reason for that is because then if we need to do mathematical operations on this, it's easier to deal with 7 radical 5 than radical 245. All right, well, that was fun. I think you'll agree. Yes, I mean, it's as much fun as, fun by math standards. Let's put it that way. All right. Does anyone here not enjoy simplifying radicals? Oh, it's fun, isn't it? Yes, it is. It's so satisfying too, isn't it? It's like when you see a mess and you clean it up. Isn't it nice? Yes. It's not terrible. All right. Well, I'll take that. Yes. So yes, we did have that discussion about Pythagoras last time too, and his cult. Oh boy, they would have been horrified by some of these numbers. Yeah, they had a different outlook and everything. But in ancient Greece, geometry was king. A lot of what we do now, the algebra and the trig and all the rest, was invented much later. In fact, calculus wasn't even invented until the 17th century. That shows you how long it took, because in the early days, it made sense. Geometry, because they're trying to analyze, for example, how to build a building properly and how to plant crops efficiently. So geometry was really the most important branch of math in those days. And but like Archimedes and people like that, they only wrote in terms of geometry. Okay, now multiplying. If we can, I mean, this here we're focusing our attention on simplification. Now we're going to see that we can actually apply algebraic operations here. So can we multiply radicals? Yes, we can. And again, part of the motivation is to simplify them. If you notice these two radicals, we have a C and we have a D. So here we're literally just rearranging it. And then of course, these two can be consolidated into a single term, radical AB. Now, when we have actual numbers, we'll see if this helps simplify it or not. But it's important just to be aware that this is what happens when we multiply them together. Okay, now, again, it doesn't always make sense to do this. It depends on what numbers we have, but it's important to be aware that we can do this. And it also goes both ways. If you started with this expression, you can work it backwards to what we have over here if there's some good reason for doing it. Okay, but it makes perfect sense. There's nothing mysterious about what we just did, but this wouldn't have made any sense unless you were aware that these are equal to each other. Okay, that had to come first. All right, so let's see what fun things we can do with the multiplication of radicals. All right, are we ready? Yes, we are. I mean, it is Monday morning after all. What else would you be doing on a Monday morning besides math? So here's some classic examples. And so, yes, so here you can, oops, let's see, does anyone have to say anything? Okay. So yes, of course, the 3 times the 4 becomes 12. And then here, 2 times 6 is equal to 12. Now, at this point, if 6 was not, if it had factors of which one was a prime number, I mean, a perfect square, we could simplify it further, but that's not the case, okay? So just be aware, the 3 and the 4 give us the 12, and under the square root sign, the 2 and the 3 give us the 6. Now, down here in the second case, the 4 and the 7 are multiplied to provide us with this 28. And under the square root sign, we combine the 5 and the 3. All right, so it's getting a little messy here. Let me kind of get rid of some of these guys. Hopefully, though, you can see how this came about. All right, and then in this last case, same thing. The 8 and the 5 were multiplied to give us 40, whereas the 2's provide us with a 4. But this time, something's different because we have a perfect square. We can simplify this to 40 times 2, and this is now 80. So imagine yourself going to a store and you want to buy, let's say, a lamp, a really nice lamp for your room. And you look at the price tag and it says, do you scream? No, you say, oh, you mean $80. That's fine, I'll take it. Wow, do you think that would confuse the customers if they wrote it like this? Yes, they'd lose all their business. So, but not to people who are in the know like us. But everyone else would say, I don't know what that means. Let me get out of here. So yes, these are the same thing. And of course, you'll agree, this is much, much simpler than this. All right. So if we can multiply, can we divide? Of course we can. The only constraint, of course, is that b can't be 0. All right. We already know division by 0 is not allowed. And so we can easily split up a ratio into its component radicals. And sometimes, again, this will help us simplify our results. All right, so let's look at some examples. All right, now, in some cases, now, like here, for example, yes, this is true, but in practice, if you had this result, you would actually write it like this. In other words, having a ratio of radicals is kind of maybe, I wouldn't say frowned on, but most of the time we would prefer to have everything under one radical unless this simplifies the results. Like here, this was a good decision. You see what we did? We took these and consolidated these into one fraction, which is clearly 2, and that reduces to radical 2, which is much cleaner and simpler than this. And in this last case, wow, now we did some serious simplification. I took the 2 radicals and turned them into a single ratio, which reduced to 1/4. And of course, both 1 and 4 are perfect squares. So this simplifies nicely to 1/2, and my final result is 5. So again, it's the same idea. This is much, much simpler than this. All right, so that's kind of nice. So basically, as you can see, we can always multiply and divide radicals. Of course, we have to avoid division by 0. Adding and subtracting, though, is a little bit different. It turns out that it's not always possible to add or subtract radicals. There's certain conditions that have to be met first. All right, so that's why we saved it for last, by the way, because it's a little bit more complicated, surprisingly enough. So here's why. If you notice, this is probably exactly what you were expecting to see. I combine the A and the B, but you notice I'm adding them because this is addition. And if you notice, they both have the same radical. And then with subtraction, exactly the same. It's now A minus B. And they both have the same radical. Now, the reason why that matters is because we can only add and subtract numbers with the same radical. Okay. This will make more sense when you see some numerical examples, but you can see the logic behind this, I'm thinking. But now we have to see how this works and why it only applies when they have the same radical. So here, that is exactly the case. They both have radical 2, so therefore we can consolidate the 3 and the 4, and we end up with 7 radical 2. Now, this is a good move. This obviously simplifies our result, and that's a good thing. And the same thing with this subtraction. I'm subtracting, I got 5 radical 3 minus 2 radical 3, and I end up with 3 radical 3. But what if I had something like this? What if I tried to do this? 3 radical 2 plus 4 radical 7. Can I actually add those together? No, because the radicals are different. In fact, it's really no different. Imagine if you had, like in your shopping bag, 3 oranges and 4 apples. Is there any way you can combine those? No, because they're 2 different things. Oranges and apples are not the same thing, and neither are radical 2 and radical 7. So in order to add or subtract, they have to have the same radical. And so in a case like this, this is how we would have to leave our answer. Just like that. There's nothing that can be done with it. Okay. But I think that makes sense to everyone. It's intuitively, it should be clear why we cannot simply add those together, because they're not the same object. Okay. It's like, again, it's like 3 apples and 3 oranges and 4 apples. You can't add them together. It would be different if there were 3 oranges and 4 apples. 4 oranges, but that's not the case. All right, now we're going to look at a technique which helps us simplify our results, but in a very specific way. And this is referred to as rationalizing the denominator. Basically, the logic here is this. Whenever possible, I'll add this at the bottom. Whenever possible, the denominator of a ratio should be a rational number. That's sort of a rule of thumb. In other words, just to keep things simple, we're going to try to avoid having radicals in the denominator. Now, you might say to yourself, does it really matter? Well, yes and no. I mean, it's more of a matter of convenience. But the way we do this is something that's actually quite interesting. Okay. And you might recognize having seen this before. Okay. Man, who else is? We have a lot of camera shy people in this group, I see. That's okay. Now, let's take a look at some examples. For example, I've got 1 over radical 3. Now, because there's a radical, remember, radical 3 is irrational. And I would prefer not to have it in my denominator. Here's an interesting technique. I can multiply any number by 1 without changing its value. The clever part is the form that I choose for my 1. Is this equal to 1? Yes. Why did I choose that particular version of 1? Because look what happens. In the denominator, when I multiply radical 3 times radical 3, I end up with 3. Nice. In the numerator, I have radical 3. So these are the same thing. But guess what? Here, this is the preferred form because there's no radical in the denominator. So you ran into this a lot when you're studying trigonometry in high school, when you're looking at like sine of 90 and the cosine of 30. Often they were radicals, weren't they? Yeah. Those are the days, huh? So don't be frightened. We're not going to do any trigonometry in this class. Okay. If you wanted to be an architect or something, then you would need this trig, but no, I don't think so. And in the second case, look how nicely this worked out. Not only did I avoid having a radical in the denominator, I actually ended up without a denominator at all. 12 radical 2. That, I think you'll all agree, is much simpler than what we had in the first place. But the whole thing is I want to multiply this by this square root or radical over itself. And this is how the technique is accomplished. So the choice is always simply this value divided by itself. All right. Now simplifying, now we already have this expression, we already know this. Here we're just going to try to focus our attention on finding techniques for simplifying our results. So look at these cases. Now here we got very, very lucky, didn't we? Because we have a ratio of perfect squares, this reduces very nicely to 5/3. Now, normally you would not divide one by the other. 9 does not divide evenly into 25, does it? And yet still we were able to find ourselves with a nice result. We have a ratio of 2 rational numbers. Same thing here, 36/49. It's nothing that could be reduced, but by splitting it up into 2 radicals, look at how nicely this turned out. Yeah. We should be applauding right now. Good. Okay. Okay. Now, I think you'll find this very interesting. And by the way, we're going to see a video about this in a bit. This is an application of radicals. This is a very fun concept in math called the golden ratio. And you notice it consists of a square root. This, by the way, this is the Greek letter phi. It's spelled phi, but it's pronounced like phi, basically. And this is called the golden ratio. And it was discovered in the Middle Ages. And it turns out this is very useful. Oh, by the way, when was the last time you saw this symbol? These curvy equal signs mean approximately equal to. The actual value has an infinite number of non-repeating digits. So in other words, phi itself is irrational. But it has a lot of applications in the real world. Now, some of these you'll recognize. It's been used extensively throughout architecture, painting, sculpture. It often appears in nature too. Now, it makes its appearance in a book and a movie that were very famous when they first came out. I'm going to say in the early 90s. Yeah, it would have been no, maybe not. No, it may have been the late 90s. Now that I think about it, early 2000s. Let's say it's been about 20 years. And I'm going to write this down. And I'm going to see if this rings a bell with anyone. If you're a big reader, you might have encountered this book. This book was written by an author named Dan Brown, and it was called The Da Vinci Code. Okay. Now, of course, there was a book first, and then it was made into a movie with Tom Hanks, which, if you've never seen it, you should move that up your priority list towards the top. Okay, because I'm sure you have a bunch of movies in mind that you want to watch, but you haven't quite gotten around to. Well, I'll tell you what, put this at the top of your list. All right. It's not only fun, but it's actually a learning experience too. There's a lot of useful information in there about math and code breaking and Leonardo da Vinci himself and his works. It's just fun. It's just well done. But a large chunk of the plot, believe it or not, revolved around this golden ratio. It's hard to imagine that a novel could be based on the golden ratio, but that's exactly what ended up happening. So, and we're going to see in the video more discussion about this. But what I just want to show you is some of the most important details. The golden ratio is derived ultimately from what we call the Fibonacci sequence. Now, does that look familiar at all? You may have encountered this in school. What's going on with these numbers? Is there a pattern there that we should know about? Good. What is the pattern? Does anyone remember? Well, if you start with the first two numbers and add them up, they'll give you a 2. If you then take the next two numbers and add them up, you'll get a 3. And then if you add up the 2 and the 3, you'll get a 5. And so that's how the sequence is being generated. Each term, except for the first two, each term is the sum of the previous two terms. This was developed by Fibonacci. The Fibonacci was the name that was used by an Italian mathematician named, I think his name was Leonardo da Pisa. Anyway, it turns out he actually was friends with Leonardo da Vinci. And in fact, if I remember correctly, when he wrote a book that da Vinci illustrated for him. But anyway, now what does this have to do with anything? We're going to see in a second how if we take the ratios of consecutive terms, the limiting case for these ratios is the golden ratio. And then once we have it, you'll see that there's a lot of ways in which it can be very useful. Yeah, not DiCaprio. No, that was a little later. This is like the 1400s. So I think it was a little before Leo's time. All right. So if I take the ratios, now again, these are the Fibonacci values. Remember, there's 2, 3, 4. So if you take the ratio of let's say, remember this, the terms are 1, 1, 2, 3, 5, 8, 13, 21, 34. What I'm basically doing is taking the ratios of two consecutive terms. That's right. That's what you call a long distance relationship. And you notice I keep doing these calculations and look what happens. And so those numbers are getting closer and closer and closer to the golden ratio. Okay. In fact, if you threw this into a computer, you'd see that eventually this is where it's heading, towards the golden ratio. So I'm going to show you just a handful of applications. The video we're going to see has a lot more, and they're really cool. I just found a few that I put into the slides, but when you watch the video, it'll be very, very impressive. All right, you'll say, wow, who knew? This is so amazing. Be prepared to be astonished. Okay, all right. So let me show you some examples where this pops up in art and in nature. Now, sometimes it's a bit of a stretch. In order to convert this into art, what happens is, well, you'll see, we can create this special diagram which generates a curve or a spiral. And it's that spiral that's being used in art and potentially in nature. Here we go. So this diagram, what they've done is they've created a series of boxes. Now, if you might recognize, it's hard to see, these first two tiny little boxes are 1 and 1. So what they've done is they've constructed this very special diagram where the areas represent these numbers. And by constructing them this way and by connecting them, you've got this spiral, which is sometimes called the golden spiral. And it's this that we're going to see showing up in art and in architecture and in nature. Now, some artists do explicitly use math in their work. So others, it may be more subconscious, but it's a very interesting area. In fact, there actually are books that have appeared on the New York Times bestseller list about the golden ratio, if you can believe it. Occasionally, you know, math books sometimes do sell very well. In fact, I remember one year, there were actually, at one point in time on the New York Times bestseller list, there were actually two bestsellers, and they were both about prime numbers. That's right, prime numbers. People were reading books about prime numbers. So, and they sold well. That's the surprising thing. You never know when you might catch the public's fancy. I mean, certain topics are fascinating to people, and you never know what they might be willing to read. All right, so let's see how this works. By the way, if you're actually studying art of any form of art, graphic arts or anything along those lines, you may have actually bumped into this before. I don't know. I don't know exactly what you're covering in your art classes, but my guess is that sooner or later something like this might show up. So let's see how that works. Look at that seashell. Now, does that not remind you of the golden spiral? Yes, it does. Remember when you're a little kid holding it up to your ear to hear the ocean? How cool was that? Okay. How about these flowers? Oh, this is a seashell in the left. Look at all those spirals. Do they not remind you of the golden ratio, the golden spiral? Yes, they do. How about the ear? Isn't your ear very much like the golden spiral? Why, yes, it is. So what else do we have? Look at this staircase. Isn't you think the architect was using the golden spiral to design this thing? It's possible. We don't know for a fact, but it looks like it. Wow. What would be the point of doing that? Well, apparently it makes it so that it's not so steep. It is. It really is interesting stuff. But wait till you see that video, then you'll really be blown away. All right. How about this famous lady? Who is this lady? I don't think there's a single person on the face of the earth who doesn't know Mona Lisa. That's right. There she is, staring. You notice those eyes never leave you. She follows you wherever you go. Oh, she knows. She knows everything. She sees into your heart and she knows what's going on. So how about, remember, Da Vinci knew Fibonacci, so it's possible that he did, at least at some level, incorporate that into his paintings. Now, sometimes what they'll do is they'll take the boxes from the spiral and show you how the proportions match up with a painting like this one. Now, in the Da Vinci Code, this painting was really at the heart and soul of the mystery. There's a lot of discussion about the Last Supper. And if you look at these boxes, apparently they all line up with the golden ratio. Now, of course, you know, the sad thing is, you know, Da Vinci was a big time experimenter. He loved to try new things. He was good at everything. And he was constantly learning and developing new things. He decided when he painted this thing to experiment with a new form of paint. So he's painting this wonderful fresco on the walls. And by the time he was finished with it, it was already starting to sort of fall apart a little bit because he incorporated beeswax into the paint. So for the last so many centuries, scientists have been working like crazy to figure out how to keep this thing from falling apart. But there it is. Okay, so if you've seen the movie, you've read the book, or if you do, this is a hugely important component of the plot. That there's like he's essentially saying, listen, um, who is this guy right here? There's one mystery character in the painting that is part of the mystery of the story. All right, well, I don't want to spoil it for you in case you decide to read it this weekend. This is his very famous drawing called Vitruvius Man. He was extremely skilled at drawing the human anatomy. He was a scientist as well as an artist, and he really understood how anatomy works. And so these ratios, of course, are all golden ratios. And then this was done by a computer in the 20th century. Oh my God, how cool is that? Yeah. By the way, you know that you can print this out off of your slides and hang it up in your room. Yes, you can. Like I said, if you're studying graphic arts, you can actually do this too. You know, if you have Photoshop or whatever happens to be the case, Adobe Illustrator, this really is more. Yeah, this was generated by a formula. Um, so some artists are also good at math, and they're able to create these spectacular shapes using just numbers. And so you can see the result here is quite cool. Are you tempted to print it out at least? How cool would that be in your room? That's right. The formula knows. It's like if you're trying to generate snowflakes, formulas will probably do a better job than you might be able to do by hand. That's for sure. But anyway, so now with all this excitement here, why don't we do this? Let's go to the Moodle and let's take a look at this video, which I put there. And again, remember, I'm going to have to turn off the recording while we do this. So you'll watch it on your computer. It's right here. And I'm going to send you, just in case you don't have Moodle open right there. Oh, but you'll like this. All right, I'm going to send you the link in the chat room so you can watch along at home. All right, and so I'm going to turn off the recording, and then we're all going to watch it because it's so much fun. Is everyone finished watching it? Good. Wow, that was pretty cool, huh? Yes, it was. You can see that this Fibonacci thing and the golden ratio, wow, they can be derived in so many different ways, and it shows up in so many different places. So yeah, it's one of those interesting things about math. You find these every so often, and this is one of the more famous ones, especially because of the connection with Leonardo da Vinci. That makes anything important in math. Okay. So wow. Woohoo. Anything that comes after this will be kind of anticlimactic, don't you think? Yes, but we do have a couple more that I think you'll like, even though they're not as cool as this. They're still important and they're still interesting. All right. I've got two more for you today that I think you'll like very much. They're tying in directly with what we've been doing before we got to the radicals, that is. And so why don't we check these out? The next one, I will go back to Moodle and I'll send it to you. This one is called Making Sense of Irrational Numbers. Remember, we mentioned this thing about Pythagoras and his followers. They were not happy to find out that radical two is an irrational number. So we're going to take a look at this video called Making Sense, because it is a very strange concept. All right, so let me send that off to you right now so we can check this out. All right, come on. All right, there it is. Let's check this out. I will, in the meantime, of course, turn off the sharing and let's take a look. Okay. Wow, that was interesting. So yeah, he was one of Pythagoras's followers. And remember, this in this point in time, their entire worldview was based on the idea that all numbers are rational because everything is formed from perfect shapes like perfect squares and perfect circles. And to find the existence of an irrational number meant that everything they believed in was wrong. And so you can imagine why that was a real problem. It's like, so yeah. Now I don't know about that stuff about the gods punishing him, but yeah, that was quite a big breakthrough. But like I said, the other followers didn't think that this would go over too well with the general public, so they tried to keep it a secret. But these guys were serious. When you have a motto, all is numbers, you know you take math seriously. So you don't. This is not something that you're going to put up with lightly. The idea that there is something out there which contradicts what you firmly believe in, and so you can see why this was such a real problem for them. And so I'm not quite sure when all of this actually made its way into print, but this is where they developed this idea of irrational numbers in ancient Greece. One of the followers of Pythagoras, who would have been very upset to learn about this. So, all right. Anyway, now I've got one more here, which I think you'll like very much. It really ties together a lot of what we've been doing in a very interesting way, including how do we think about imaginary numbers? Okay, he's going to try to show you graphically how you can think about it. Oh boy. All right, I actually hit some button I shouldn't have. All right, so the last one is here. Let me go get it off of Moodle. Let's see, now I lost it. Here it is. This one is called Why Are There So Many Numbers? It sounds like an interesting title. Um, and this one is very well done. You'll have fun with it. All right, here we go. All right, let's check it out. All right. How was that? Yes. So now you have a way of visualizing what imaginary numbers are supposed to look like. It's just a separate dimension. It doesn't have anything to do with the real number line. Very well done. You can see this guy cares about math. I mean, you can tell he's very excited about it. And so they did an excellent job of tying together all these concepts that we've been covering, but in a way you can visually see them instead of just writing down equations on a piece of paper. So I think, yeah, that was exceptionally well done. So, all right, well, that was fun. Now we've got a little bit of time. We can go back and maybe get a little more work done on our radicals. All right. I know it's sad we have to go back to it, but don't worry. There's plenty more fun videos I'll have for the rest of the course. The great thing about YouTube is yes, there's a lot of crap on it, but there's an awful lot of really good stuff as well if you know where to look for it. So, all right. Anyway, so that was, by the way, that was 5B. Now we're ready for 5C. Okay. And so let me go get that open here. Man, we're just zooming along here. We're already starting 5C. So fairly soon, what we're going to do is start working on problem sets where we can get some practice with these concepts. So we'll worry about that later on. But by the time this chapter is done, I want us to get some practice, because while this is interesting, you won't ever know if you really get it until you've actually worked on problems. So that will be coming up very soon. All right, so here we go, 5C. Now, you would think that there's nothing left to say about the real numbers, but you'd be so wrong. Okay, there's a lot more fun things to say about the real numbers. What's today, the 8th? Yes. All right, so now we're going to look at some basic properties of the real numbers. And we've already seen that, the real numbers actually, we've been using this symbol, fancy R, to represent the real numbers. And remember, we wrote it out like this once: the rational numbers and the irrational, we put a union sign there. And we've already taken the rationals and broken them down into integers and whole numbers and all the rest of that. Okay, remember, this means union. And so what we're doing is creating a new set which consists of all the rational and irrational numbers, but you notice that these have nothing in common with each other. They're two completely different sets of numbers, but all of them are real. And all the real numbers fall into one of these two categories. Now, we're going to look at some basic properties of the real numbers. Now, some of these you almost certainly have heard of before, and some of these, well, maybe not so much, but that's okay. We're going to do them all right now from scratch. I'm going to pretend that you've never heard of any of these terms before. So let's take a look at the names, and let's see if they look familiar. Now, I'd be willing to bet that you have at least seen these two. Yeah, they should look very familiar. But now it's possible that you've forgotten what they mean, but that's okay. It'll come back to you very, very quickly. And none of these are very complicated, and pretty much all of them are just, to me, just common sense. But if these properties are not well defined, that would make mathematics much more difficult. So a lot of what we'll be doing is based on the idea that all of these properties have to hold for all real numbers. And in fact, a lot of times when we're doing algebraic operations, we're actually using these properties without thinking about their names. We're not thinking consciously about the properties that we're using. We're just doing what seems natural. All right, it's kind of like when you're speaking a foreign language, you don't really think about grammar as such. You're just using the words. All right, but anyway, there's three more. And I'm sure that of all of these, you immediately recognize this one. The others, maybe, maybe not. It depends. Well, let's go through them. And some of them are extremely basic and some of them are a little bit more involved. Okay. For example, the first one, the closure of property is pretty simple. It almost seems like it's unnecessary to even formally state this, but we do. So let's see what this is all about. Here's what it means. There's a closure of property for addition, which says if I take any two real numbers and add them up, their sum is also a real number. And that's all it is. In other words, you can't actually create an imaginary number by simply adding together two real numbers. So like I said, doesn't that seem like common sense? But we do have to formally define it this way. We have to have rules. Okay, now if there's a closure of property for addition, by the way, I just want to mention here that you don't need a separate one for subtraction, because subtraction is really nothing but the addition of a positive and a negative number. So you notice there is no property for subtraction rather, because it isn't necessary. It can be considered to be part of the property of addition. And in fact, that's what subtraction actually means. You're just adding a negative number. So technically it is part of addition. Then we have multiplication, and you can probably guess where this is going. If you take any two real numbers and multiply them together, you also will end up with a real number. Of course. What else could it be? All right, and again, we don't need a separate one for division, because division really just means multiplying, like this. This is what division really means. A times 1 over B is what we mean by division. So there doesn't need to be a separate property for division, although we do have to be careful here to make sure that B is not 0. So in other words, we're basically making the case that division is a special case of multiplication. All right, now here's one that will ring a bell: the commutative property. And that just tells me that the order in which I add two numbers is irrelevant. In other words, and you know this intuitively, 2 plus 3, for example, equals 3 plus 2, because addition has this commutative property. The order in which two numbers are added is irrelevant. Now, here's a case, though, where we cannot extend this to subtraction. Why not? Because, watch this. This does not apply to subtraction, because 2 minus 3 is not the same as 3 minus 2, is it? It is not. So this one really and truly only applies to addition. And like I said before, I mean, it's like, this is, at this point, this is just common sense. You've known this since you were a child. It's almost like taking a step back and drilling down into English and wondering why certain words are what they are. This is the formerly known as the commutative property of addition. Now here we also can say the same thing about multiplication. Oh, here's some simple examples, and you notice, this is the same as this. And here we have the same thing. These are both the same thing. So does this apply to multiplication? It turns out it does. It sure does. Okay, so in other words, is it true that 3 times 4 equals 4 times 3? Why, yes, of course it does. But I'll make a note here. This does not apply to division because, for example, 2/3 is not equal to 3/2, is it? No. All right. Are there any other? Oh, that's right. There's 6 properties that we need to know. Oh, and of course, these are simple examples. And it should be clear, again, no matter what order you multiply. By the way, this can be extended to 3 numbers as well. It's not just 2, but in general, the order of multiplication does not affect the results, as you know. And again, we call that the commutative property. Okay, are we all caught up? All right, so let's see. All right, you know what, I'll tell you what, I think this is enough for today. We've got a few more properties to look at and some other interesting ideas coming up. But yeah, I think that'll do for now. We're done. We'll start next time with the associative property. And unless there's any last minute questions. And by the way, if you want to watch those videos again, they're all the links are on Moodle. Or if you want to show them to somebody else, suppose you have a friend who doesn't believe that math is cool, and you say to them, listen, I'll show you that math is cool. And you show them those videos, and before you know it, that person is suddenly going to be a math major because they saw those videos. It could happen. So the links are on Moodle in case you want to watch them again or make a note of them, or maybe favoritize them, or whatever you do, save those links. That way you can watch them again whenever you want. All right. So, all right, other than that, unless there's any last minute questions, I guess I'll just see you all on Thursday. All right.
Thank you.
You're welcome.
Thank you. Have a nice day.
Bye.
Thank you.
See you later.